Okay, so tonight we are talking about how we can improve our Rust skills by making an ECS library. Um, but first, who am I? Well, I am not only one of the organizers of the Denver Rust Meetup, but I'm also the technical team lead at Health Scholars. We do health, basically, we make health educational VR courses slash assessments that doctors and nurses can take to ensure that their skills are up to par and they're ready to help any patients that come along their way. However, I also am a live streamer on Twitch. I do a lot of live coding Rust projects, a lot of visual based things using game engines, and other interesting things. I've been in the IT industry for over 15 years, which did include 8 years as a systems administrator at NASA. And so that time at NASA was what really got me interested in like backend and basically the non-front end terminal side of programming. And I think like if I had Rust as a tool, I probably would have been too scared of it back then because I didn't really know how to program. I learned C like a little tiny bit, but I didn't get far enough in to like get the dangerous part of C. I was mostly like shell scripting, like fixing other little people's like install code that was broken, and running backup servers and every other like little things that you could possibly think of to do as a systems administrator. But now that I'm a programmer, I find it really like fascinating to sort of dive back into that area, but now with like the programming in my in my tool case, whatever, my tool set. So let's talk about like why an ECS library and like how does this like improve our skills. I'm a big proponent of when we play with something and like learn something, especially if it's outside of work time, that it be in a completely different domain. And that's because if we don't have it in a different domain, it's going to end up causing us to burn out. Like we're just going to be doing too much of the same thing over and over and over again. And then, And so even if we were building like a project for ourselves, if it's a business project, that means you're doing business during the day and business at night. That's no fun. That's Game dev to me is like playing a puzzle, a really, really hard puzzle, but it's still a game. Like game dev itself is like a game. And so I have a lot of fun with it, even though it technically is really hard. But what I was surprised about was the farther I have been delving into game development, the more I've been needing to like learn new things about programming that then opens up options for me during my day job where I'm doing a lot more web development. And ECS is one of these things that sort of like unlocked some new skills and like had forced me to go deeper into Rust. So let's talk about what ECS is. Before everything started, I had asked like, hey, how many of you know ECS? And I got a couple. I know ECS, kinda. And I think that's pretty common. It's something that is like I've heard a lot of people say. I hadn't like, but before I learned it, I didn't really like know anything more than, oh, it's something you do for speed, right? And then it really didn't go from there. So the very basic explanation for ECS that I can give is it's an in-memory database that we have in code. So I'm going to sort of describe it as kind of like an Excel document. It's a spreadsheet where we have columns and rows. So over here, we can see our entities are the columns, and our rows are the components that make up each entity. So for this example, the player has a location, an X and Y value for that. Our player has a size and a health and a velocity of like how fast they're moving. So does the enemies, but the tree, which is a background element, it has a location and a size, but it doesn't have health and velocity. We can't hit it, and the tree doesn't really move. It just sits there. And, maybe the player can move past it, but the tree is like staying still in the world. So the purpose for this ECS is to make it really simple for me to say, okay, I want to write a function that does one thing. That's going to update all of the locations. So what I need to do, I need to grab the velocities and the locations of every entity. I don't care what they are. I just need to know that this velocity matches with this location, and then I'm going to update that. And I can do a little bit of vector math. And vector math in this, in this case is just take the velocity x and add it to the x of the location, and the same for the y. And then I just need to repeat that for everything that has both a location and a velocity. So the tree, we won't be updating that at all. And this is like super common in game development, and probably common in some other data-oriented types of projects. In game development, we have like so much data we need to get through. And if we're trying to make a game run in 60 frames per second or higher, then that means at most we have 16.66 milliseconds to do all of our math calculations and draw everything to the screen. And drawing to the screen takes the most amount of time. So we have actually less than 16 milliseconds to really do all of our updates. Now, it turns out that while CPUs have gotten really, really, really fast, memory has actually not kept pace with CPUs according to like the old Moore's law. And what that really means is that if I request this piece of information, and then I go and request some other piece of information way elsewhere, it has to unload from the cache and then reload from memory. And that just takes a long time. So what most CPUs do now is they'll say, hey, you're loading up this piece of information from this vector. Okay. Or this piece of memory, really. Okay. I bet you're going to load up this piece of information and this piece of information and this piece of information. And so when you do that, suddenly now I can say, okay, give me all the locations here, and I just have them all. And give me all the velocities. Well, there's enough room for several different vectors that I can grab into in that cache. And I could hopefully minimize cache misses. That being said, this project and this ECS isn't optimized to minimize cache misses. There's a lot of really cool optimizations you can do once you get to the point where you really need to like eke out that last micro or nanosecond of performance. Other libraries like Specs does this. This does not. So what are the features that we have in an ECS? Pretty much CRUD. I mean, if we're going to have an in-memory database, we also have to do all the normal things that a database does too. And because we're writing this database ourselves, we have to write that as well. So we need to create and delete things. Okay, so insert, we just need to add another row in here. We also need to add new components. So we need to add both horizontally and vertically in this database. But perhaps the most difficult would be I need to query this. Now, we're not going to recreate SQL for this database. We're going to have perhaps more simplistic querying system. But that's okay. It's our project and our ECS library. We can support it whatever we want, and everybody else who uses it are forced to do whatever we say that they have to do. Now, for me, our requirements are I want all entities that have locations and velocities, which means that when I query for location and velocity, I want player, enemy, and another enemy. I do not want the trees data to come here because it doesn't have both a location and a velocity. So during this talk, we'll probably spend a bit of time talking about exactly how our query system is going to do that. And then finally, we need to update this information because if it's just static, then there's no reason for it to be a database. It could just be a JSON file, we load it at, load time. But no, we need to be able to update this live at runtime. All right, so let's dive into it. What does a system look like? So a system is really just a fancy name for a function that's going to do an action on the data in the ECS system. I actually have that right here. Okay, so this is an example of a system file that I've used in a project that I'll demo off at the end. It is using an ECS system that I built. And the ECS system that's like, that this talk is basically showing off. So I'm using zero-size structs for these systems with just a single function attached to them. I decided to do that because sometimes it's really helpful to keep systems around a little bit longer, and having systems be in a struct format allowed me to like add new methods to it if necessary. This is a relatively simple system, and it's just that same update location that we talked about earlier. So the first thing we do in here, or maybe the first thing to note here, we're taking in an immutable reference to the world. There is some reasons to do that. Is mostly it's if I have to mutably pass the world in everywhere, then I have to keep track of like which systems have the world, and make sure that they're not accessing the world at the same time. This way I can just say, here you go, have the world, I don't really care, deal with it. And then all my systems that like maybe need a mutable access to the world, which are very few, they're gonna be isolated off into their own area. All right, so the first thing we're gonna do here is we query. So notice our query is actually a builder pattern here. We'll talk a lot more about queries later on. And then I'm able to loop through all of the stuff that we get back, and then I can just, at the very end here, is the one line of code that actually does the logic for this system itself. I'm just taking the location and adding it to the velocity. Now I am doing like these double dereferencing things. That's because there's a lot of like other clever stuff happening where I'm like having to actually get access to the place in memory and like do the additions right there. Also, it has to do with what I'm doing with all this borrowing and all this stuff, but we're gonna get into what that is soon, I promise. So to do the map, to do a query, we need a map. And this actually is really important. The first time, so I built an ECS system 3 times. The first time I didn't build using any of this map technology and it worked, but as soon as I had 100 entities on the screen at the same time and they're all dying at around the same time, everything slowed down tremendously. It got really, really, really bad. And then I think I did I didn't keep it, but I did a flame graph, and we had some really nasty big O. Like I think there was a triple nested or maybe even a quadruple nested loop in there somewhere, which just got really slow, really fast. So what I learned is that I can associate every single one of these components with a mask, basically a binary representation of this specific component. So we can imagine location here is basically just all zeros but 1 on the far right. And size would be the next one over. Now notice that for each of these, there is no shared ones. Like it's just 1, 1 in the entire binary representation of that. And that's really, really, really important for this. However, you may realize that this limits how many of the components we can have to, well, how many bits our number is. If I were to use a U8, which is, this is represented here as a U8, then 8 zeros, 8 digits is all I have access to. So therefore a maximum of 8 components. For the ECS that I used a 32-bit, like a U32, but you could obviously go to U128 and just have a ton of components. And I think is there a U256? I don't think there is. I don't remember. But there are tricks where you can get like higher digit numbers, but at that point in time, you're probably slowing down enough that a different system is required. So this is what the map looks like. The player has one of everything, so we get 1, 1, 1, 1. We basically just literally saying you have a location, have a size, have a health, and have a velocity. Meanwhile, the tree only has a location and a health. It doesn't have anything else. So in order to use this map, we're going to jump into bitwise operations. The type of thing where I've heard of a lot of people having to do in like various computer science interviews and like at college, but had never found a need for it in web development, and suddenly hear a really nice use case for it. So let's take a look at how Rust handles bitwise operations, which it turns out to be pretty much exactly the same as many, many other languages. So here I have 2 mass. So we have this 0, 1 and 1, 0. To create the numbers, here I'm using U0B and then just my zeros and the 1. This tells Rust, hey, it's a binary number, but turn it into whatever you need to be. So I think by default a U32. And then I'm going to start with the map, which is just this is 0. And then what I want to do is I want to say, hey, map, I want to give you a location. So I want to take you and compare this number, the map, with this number. If ones share a position, don't do anything. But if the map doesn't have a 1 in that one's position, then give the 1 to the map. And that's what this symbol is doing, or equals, which is not really or equals, it's pipe equals. And then I do the same thing with the size mask. So we can see what our debugs happen over time as this runs. So I'm going to go ahead and run this. And we see we start with 1 because it added in this 1 in a ones position. And then we have a 3. Remember, this is a binary. So in a ones position is 1. And then in this position, it's 2. So 1 plus 2 is 3. This is going to be a clever way for us to determine during our queries, hey, what should we get? So let's go and take a look at those queries. So now, previously I was in the code for the program that was using the ECS library. This is a separate repo, which is the ECS library that I'm going to use. So I actually do have this in crates.io, and it's deployed out there. What the biggest thing to notice here is that I have a map for the query itself. So as I'm building up what I'm looking for, I'm building a map that I can compare to the map for all of the entities. Let's see. It's a very similar, if you remember what this looked like, we have our query, and then we can just run with component and pass in a type. Now, what I've decided to do is I wrapped all of my data in its custom types. And that allows me to make sure that I don't run into any problems if I have like, oh, something takes in a vector 2, let's say. Well, I create my own type velocity that's just a tuple type that holds a vector 2. And so that way I can have 2 of these that hold the same type inside, but now they're really seen as different types according to the compiler. So when this comes in, I take this type in, and I'm actually using the any trait to, I guess I'm not really paring it down or restricting it all, because any is kind of literally anything. It's a nifty trait that that doesn't really have anything on it, but is kind of fun to use if you need to do any kind of dynamic dispatch. And at that point in time, I'm able to get the bit mask from the entities, and then I just do this or equals to it. So now I know, okay, I have a location. Well, the 1 goes into the location spot. Then when I run this, it's a 1-2 pass. And so this prevented me from having triple nested loops down to only a double nested loop. I couldn't figure out how to make it just a single loop all throughout without doing a lot of extra crazy stuff. But I'm trying to keep it relatively simple, but still like decent at the same time. So the first pass that I do is I go through these indexes of the type IDs that I'm looking for. Now, every type has its own unique type ID associated with it. It's kind of like a hash of that type. Specifically, those type IDs are guaranteed to be the same on the same system at that runtime, but they're not guaranteed to be the same across runtimes or on different computers. So don't ever like debug it out and then hard code a type in, like saying, hey, if you're a U32, this is like the type for U32. You're going to have a bad day. So what I do is I loop through all of those and I grab out the type ID, and I can basically ask, hey, entity, like the actual map for each of the entities, do you have this? And that's what this and is. When I do and together, it's going to give me a number of the ones that are in the same position according to the binary, map. And so if my map after doing this and is exactly the same, then we share ones. So that means that yes, we're looking for a location of velocity. The player has both of these. So therefore, we're good. So the number behind the scenes, if we look, that's a 1, 2, 4, 8. So this would be a 9, essentially, that we're looking at. Then I create a vector of the indexes that I want to collect together. And now what I'm able to do is just loop through every single component, which, if you remember, is each row is going to be its own vector here. So I loop through each of these and then just grab out the index and just say, okay, I want you and you and you. And I just throw them into their own vectors, and I'm going to return essentially a vector of vectors. And that's how I can basically query for specific components and only get the components that I queried for, but also the entities that have all of those components. I'm also throwing in the indexes as a bonus because those are needed to be able to delete them. I need to know what those indexes are. All right, let's come back here. Okay. Let's see. Did that, querying. Okay, so you may have noticed in this query that I've done some cloning. But also, if you remember, when I'm actually running the update location, I'm updating the location based upon this. How does this work if I'm like cloning the stuff that I'm getting? In fact, I'm cloning it again right here. Like, how can I possibly clone something and then like also mutate it? Well, that leads us into some of Rust's more interesting data structures, the smart pointers. So there are some things in Rust that allow us to have something called interior mutability. Basically, I can have an immutable access to something. I can clone it as many times as I want, and then I can just say, okay, give me a mutable reference to whatever you're holding, and I grab that. So the way it works is we're going to start with something called an RC. In fact, do I have that? No, I don't. Let's see, let's come up over to entities here. So I'm going to start with an RC. So RC stands for reference counting. It's going to, behind the scenes, count how many references something has. So when I clone it, instead of it giving me like a new thing, it gives me kind of sort of a reference to a thing, but then it's going to count behind the scenes itself of how many times somebody has access to that. That way, when it drops and goes out of scope, it doesn't delete, but rather it keeps it around until the last thing gets dropped. In a way, it's kind of like how JavaScript works. Like if you have one reference to any variable, then the garbage collector is going to keep it around. It's not going to delete it until that last reference is gone. So there is a caveat though. You can only get references inside of the RC. You can never have a mutable reference inside of there. So that's where this next data structure comes in, which is the ref cell. So ref cell takes a reference to something and then allows you to borrow the contents mutably. But, and herein lies the rub, ref cell is doing a little bit of reference counting itself, and it's going to say, okay, you can have any number of references to my contents, or you can have one mutable reference at a time. Outside of that, whatever you want. But those are the rules to do. And so you notice that I put a dyne any here. Dyne, by the way, I found out it's not, it does not stand for dynamic dispatch, but rather dynamic memory. So what's really happening here is I'm storing these components in my struct. Well, the struct needs to know how much memory to allocate for its fields. So I don't know how much memory because each thing I put in is going to be potentially different. So I use this dyne any. I can't use that here because there's no way to get around it. Structs need to know how much memory to allocate. Fine, I will put it inside of some kind of structure. That structure is going to basically just sit on the stack and have a pointer to a location in heap memory, along with a size of like how big that thing is right now. And that's it. That's like all that the ref cell is. There's a little bit more of like the reference counting and other little stuff, but behind the scenes, that's kind of what's happening to things like ref cell and box, which we use all the time with something like this. But what I'm really doing is I'm moving the borrow checker actions from compile time to runtime. So oftentimes when people say, oh, there is no runtime for Rust, what they're really saying is there is no runtime that you could write better. So therefore, Rust writes the runtime for me, and it's better than I could do if I were to write it. Or at least that's the theory. So there's, let's see. I want to show you what it looks like when I'm trying to grab this stuff out here. So we've got in our velocities, our vector of velocities and our vector of locations. And if we remember, this is an RC with a ref cell and then just something inside. What I can do is I can borrow this. Now the borrow is a method on the ref cell, not the RC. RCs implement deref on them. So just like boxes, if I do any dot actions on them, so like dot borrow or dot borrow mute or anything like that, it's going to deref past the RC, goes straight to the ref cell and let me grab it out. And I could basically pretend that the RC isn't even there at this point. For the ref cell, you can see here I'm borrowing velocity, so I'm getting a immutable copy of it. or immutable reference to the memory locations. And then the locations I'm borrowing mutably. So I'm getting a mutable reference to the location in memory that the contents of the ref cell are. And then we're going to talk about the any next. So any is actually a trait. And it's one of those things where when you first hear of it, might feel like it's cheating. Like, come on, like Rust has an any trait. How is this different than like TypeScript's any type, where then you can just say, okay, you're any, and yay, I have TypeScript. Everything is an any type. Time to go home, ship it. It is a little bit different because, well, first of all, it's a trait. So it's not actually like just a full type itself. I can't actually do something like, hey, components is like an any type. That's not something that we can do. Being an any type, though, does allow me to dyn any, and therefore basically do that little bit of dynamic dispatch with almost everything. Now you may notice that inside of is it here? No, these are systems. Somewhere in here, I restrict our any to any plus static. And that's basically all of my components. I'm going to require, yes, you can be anything, but you also have to be static. That's it. That's all I care about. Any and static. And I do actually need to have the any, so that way I can do interesting things like type ID. So I mentioned before that type ID allows me to get the hash of the type. Well, I'm using that hash as the key in the hash map that stores all of our components. So that way I can just say, okay, well, all the locations, type ID locations, followed by vector of all of the actual components that make up that location. Now, there is like a potential problem with this, is that when I put it into this any type, how do I get it back? Like Rust kind of doesn't know what type it is as soon as I like basically put it into this format. And the reason why I can't just say, hey, give it to me back, is Rust implements something called type erasure, where any type that I'm not using, Rust just removes, and it's not going to be in the final binary. Like there's good things about that, but also potentially I can't just say, hey, remember what you were? Just be that again. It just literally doesn't know if the thing that it was is something that it still knows about. So coming back to our system here, the way to do this is a downcast. So I have to manually tell Rust, here is the type of the thing. Go ahead and attempt to bring it back from the any into an actual discrete thing. So I downcast a ref. It's very similar to the borrow. Ref will give me a immutable reference to the thing that I'm getting out, or I can downcast mute to get a mutable reference to it. Now it gives me an option as a result. So it doesn't just crash if you try to give it the wrong type. It might just give you a none if it's the wrong type that you're looking for. In this case, because I designed this database and I built it and I'm putting things in like the specific order and I know how it works, I am extremely confident that this, like what I'm getting out, is exactly what I put in. So I'm actually converting this option into a result. So that way I can just have this nice pretty error saying exactly what happened. So in that instance where I didn't do it correctly and I like accidentally put a location into the velocity spot, or I flipped these around and I grabbed the velocity when I actually asked, the orders are different, I will get that error really quickly and I can come in and fix that. And so that's what the any type is allowing me to have. Now, once again, this is all runtime stuff. So therefore, this will always compile despite it maybe still crashing at runtime. But that's the trade-off that we give is, well, hey, just do more work later. So let's, like, we've done a query and we've gotten out, and then as part of that, we also got updates because, well, the ref cell. So let's talk about deleting, because deleting is one of those things where, okay, now I have to go through, like, find the index. Well, okay, I already passed the index, so we just, find all the components, and then for the index, we'll set all the data to none, right? Well, not exactly, because we have a map. So what I can do is in here, I'm just going to have a function. I have two types of deletes that I can do really easily because I'm using this bitmap. I can delete a component for an entity. And notice I'm not setting data at all. What I'm doing is I'm just taking in the index and I'm taking in the type of the component so I can get that type ID, extract out the component. Oh, I don't even have to extract out the components. I just need to get what the bitmask is, so that binary number. And then I just do this bitwise operation on the map to basically remove the 1 from that digit and just say, yeah, you don't have that anymore. And then, just like old Windows disk drives, and really just modern ones too, I just leave the data there. I just let it sit there. I don't care about it. That means that the deletes are really, really, really fast. And on top of that, these bitwise operations are pretty much as close to what the CPU wants to do and like the type of math it's really, really good at. So therefore, it's like as fast as the computer can possibly go. I can delete everything near instantaneously. And the same thing happens when we do delete entity by ID. I just need to just go grab the map by the index and set it to 0. That's it. I just deleted it. Now, to use this properly, when I do insert things in, it would be really helpful if I, let's see, create entity, here it is. I actually loop through and I find the first empty bitmask. So that way I reuse the data in the database in the case that something has been deleted before. So let's say that enemy's been killed, my main character jumped on it, smashed it, moved on, and then later on another enemy spawns. It will take up that same location in the database. That way the database will only ever grow to as many entities as I need to track at the same time. And that's how I can get super, super fast deletes and fast creates. So what can I actually do with this? This is probably not very impressive here. This is a screenshot of a zombie simulator that I created with this ECS system. So let's go ahead and actually bring this out and run this. So to begin with, what we have here, let me cover that up so that way it's easier to see. All the white dots that we see here are humans. They're running around randomly as we are wont to do. And we're also trying to avoid each other because, it's COVID time. We can't, we don't want to actually touch anybody. And then that's it. That's our life, is just moving around. So then I can click anywhere and I'm going to create a green zombie. And our zombie is immediately going to be attracted to literally everyone that they can see. Humans can't see very well because we're not very perceptive. We're just looking at our phones constantly. And the zombie is just going to run around until finally grabs a human, eats the human. And so you can almost imagine what's happening is I'm doing all of these different queries for what's happening, update where I want to go, what my target is, more systems for like updating my location, updating, like drawing things out to the screen, calculating how long I have, how long I'm dead for before I resurrect as a zombie, what my type is, like, am I a human or am I a zombie? And then because of that, I'm able to query for everything slightly differently, and like, and then this is like the end result. So pretty much any type of game or visualization where you have lots of things moving on the screen at the same time, and you need to like potentially delete, update, create just like very quickly. Especially in Rust, you can run into a lot of problems where, hey, I need like all my entities. So I will loop through entities and pass in the same list of entities elsewhere. It's like, it actually runs into a lot of trouble. ECS makes it really simple. We can see that almost all the humans are dead now. Just that last one, who, yeah, I never said they were very smart. There's not really any AI in here. And that's it. You can find me at twitch.tv/bookcircer. And I'm also on Twitter and GitHub, where all this code is. I will post a link to these slides also at the end, along with where the code is. So with that, does anybody have any questions?
Is looping through components like free?
I mean, so looping through components, are you talking about like here, like where I'm looping through these components?
Like, so for example, if I have like 50K entities, and like the code is running on a server, and I have a system which like updates all the positions and velocities, and then I have another system which like sends all these positions to all the clients. So I would have to like create two loops for that.
Oh, okay. So the ECS system works extremely well with like any kind of like message passing architecture. So it's not free to loop through, but it's extremely cheap to clone, if that makes sense. So because I'm cloning and they're RCs, I'm really just cloning like a pointer towards a location in memory. So that's almost nothing. So then I just do another loop through that, and it is really fast, but sometimes like it generally that won't be your problem, or like won't cause like issues. So I would say, like, if you can do like message parsing, message sending, like event sending, or like observer system or something like that, that can help out a lot here. But then at the same time, probably build it and then take a look at like a flame graph or some other profiler and actually see if that's really where a lot of time is being wasted. Most likely not, unless your components are really big or you have a ton of them.
Okay, thank you.
Any other questions? All right. So on my YouTube, which I'll also put a link to everywhere. Come on, zoom out of my way. Okay, or can I do this? Tomorrow morning, I am going to be a guest at DigitalOcean's Cloud Chats. We're going to be talking about code spaces, releases, and a little bit of Rust. And then something else is I've created a course for like this ECS system. I only have like a trailer for it up right now, but it's on my homepage, and I'm going to be uploading more of those, like an actual walkthrough of like how I created it and a deeper dive into all the individual parts for to make this an ECS system like this. So with that, thank you everybody for coming by, and I hope that you all have a great night.
Thanks for the talk. It was really interesting.
Thank you for coming. Yeah.
Yeah, thanks you for